So last time in lecture, we were talking about the three different laws. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And all of those laws talked about the behavior of atoms. So you had a certain atom and it acted a certain way. In elements, atoms are always the same. Atoms of different elements are different from one another. Atoms exist as the smallest unit of an element and so forth. So we talked about all those things. Now what we're going to do is we're going to skip forward in history about 100 years. A lot of that work was done around 1800. We're going to go forward to about 1900 now. And science has evolved in a lot of different ways. And one thing that's now available to us is electricity and batteries. And because electricity and batteries are available, we can start doing a lot of things we couldn't do before. And because of that, scientists were now able to figure out kind of the makeup of atoms. So the next section that we're going to talk about is going to look at three different experiments that scientists did to understand what makes up an atom, why atoms behave the way they do. And the first one is called the cathode ray experiment. This was done by Thomson in 1897. Now, what he did was he basically discovered cathodes, they're called. We know them by a different name now. But here's the setup of the experiment. You've got a glass tube that's under vacuum so air doesn't get in the way. You've got one piece of metal here and another piece of metal here. When you pass electricity through it, he could see that beams of something left the negative charge plate and went to the positive charge one. So little beams or particles of something left here and went over here. The tube was actually coated with something, and that's how you could see them as they were going through there. So they were zipping through there, and then once he put a magnetic field close to it, he saw that these particles bended towards the positive plate. So some sort of particle was leaving metal, and it was curving towards a positive plate. Now, you thought, well, that's interesting. What will happen if I change the metals? So he changed the metals, and he saw that the same particle was being ejected out of the metals. So he changed the metals again, and the same particle was. So he knew that it wasn't atoms being shot through this tube because they would act differently from one another for each different element. It's got to be something else that's present in all different metals that's ejected out and then curves towards the positive thing here. He called them cathodes. Nowadays, we actually call them something different. So it's a particle that's present in all atoms, and it has a negative charge on it, so that it's directed towards the positive plate. What do we call the negative particle of atoms? Electrons. And this is actually the discovery of electrons. What he found was that as he passed electricity through the metal, electrons are ejected out of the metal, and then they move towards the positive. If you put a magnetic field here, they're actually curved towards the positive of that. It's the same thing as magnets when you're a kid. If you've got a plus magnet and a minus magnet, they're attracted towards one another. The same thing happens with charges. If you have a negative charge something and a positively charged, they're attracted towards one another. And this absolutely works this way. You can find YouTube videos showing you this. And they'll move the magnets and you'll see this light beam bend. I shouldn't say light beam. Beam of electrons bend and so forth coming out of it. So from this result was the discovery of electrons. And it was interesting for a variety of reasons. Largely due to the fact that all metals that he tried, all the different elements that he could try, all showed the same particle coming out of them. So he knew that it must be some underlying particle in it that was coming, and that was the electrons. He knew that they were negatively charged because of the way that they bended, and he had a rough idea of the mass. He couldn't separate the mass and the charge from one another, but he knew the ratio between the two of them. from this experiment. And that actually comes from the mathematical modeling of the curve, which we're not going to go into at all. Okay. So the cathode ray experiment is actually the discovery of electrons. And once he discovered electrons, he tried to explain the atom as this. This picture here is called the plum pudding model. I've never had plum pudding. Anyone ever had? It's an English dessert or something. But what it means is that you've got some positive stuff that makes up the bulk of your atom, and then you've got little tiny bits of your negative electrons mixed into it. And this was the model that derived from the cathode ray experiment. It's actually very, very wrong, but it's one of the first models to try and explain what actually makes up atoms. As a side note to this experiment actually discovered X-rays as well. So when these particles are zipping down between the plates, if it zips down and then hits the metal plate here, there's a lot of energy from its motion that's stopping, and that energy has to go somewhere. So what happens is, as your electron zips down, when it hits this plate and stops, the energy goes off as X-rays. And then this led to the discovery of X-rays that we use quite a bit today. Questions about that? So all of these experiments are actually very simple. They're not advanced in any way, shape, or form by today's standards, but they were able to figure out some little part of the atom as we're going through it. Okay, so that's the first one. It's the cathode ray. Here's the second one. This one is the oil drop experiment. And this one's my favorite for a lot of different reasons. One of which is, right here, they call this an atomizer, but it's a perfume bottle. It's a fancy name for a perfume bottle at the time. So what is happening in this instance is you've got oil that's sitting in our perfume bottle, and then we spray it out. As the oil leaves the nozzle here, it rubs against the sides of it, and it picks up an electrical charge. This is the same thing as, I don't know, do any of you have little brothers and sisters? I have a little brother, and I used to torment him nonstop. When I was a kid, I used to, in my socks, rub my feet on the ground, and then put my finger up next to him. What happens? It shocks him, right? This is the same thing that happens here. Just like with our socks, when we rub it on the ground, we build up an electrical charge. As the oil droplets go through the nozzle, they pick up an electrical charge. And that electrical charge is electrons. I didn't say it in the previous slide, but electricity is just flowing electrons. That's all electricity is. That's why there are two prongs on the outlets, because one is taking electrons out of the wall and taking it to whatever is doing the power, the vacuum cleaner, the blender, whatever, and then the other one is returning electrons back in. So it's picking up this electrical charge and electrons. So there's some electrical charge on our little tiny oil drops here. They're falling into the bottom chamber, and this hole is supposed to be a lot smaller, but it's drawn bigger so you can see it. And they're falling down into here. Now, in the bottom chamber, we have an electrical field. So if I draw this on the board, here's the bottom chamber. And we have a positive charge at the top and a negative charge at the bottom. So these oil droplets come in, and they have a negative charge on them because they've got extra electrons. So as it sits here, what's going to happen in relationship to the positive? Is it going to be pulled towards the positive or pushed away from it? Pulled towards it. So you're going to have a charge effect pulling it upwards. And actually, you've got the same charge effect from the bottom, because two of the same charge don't like to go towards each other. Like if you try and push two north magnets together, they repel each other. The same thing occurs here. So you've got an electrical charge that's actually being pushed upwards by this electrical field. But at the same time that that's happening, you have gravity pulling it down. Now what's cool about this experiment is by changing the charges on these things by just a little dial, you dial the charge up or down or whatever, and when you hit the right value, this oil droplet is going to float right in the middle. And it will just sit there. So in that picture there, we have a microscope set up on the side, and you look in with the microscope and you watch the little oil droplet just float in midair there because of these charges associated with it. So it's sitting there floating, and what that means is that the electrical component is equal to the gravity component. Because the force pushing it up and pulling it down are equal to one another, so it just sits there and floats. Well, gravity is very, very well understood. So because we know this side, we can figure out what this side is. And by doing this, we found out a couple things. We found out the charge of an electron and the mass of the electron. And you can figure this out mathematically. There's a variety of ways to do it. But in the end, the important thing is this experiment actually showed us the charge and mass of electrons separately from one another. And I like it because just imagine this little oil droplet floating in midair, just hanging out. Now, I guess questions about that? Yeah.
Well, it's not really a question. Based on
Yeah.
like, so let's say like this is on an exam or whatever.
Mm-hmm.
Would you ask like how would it work? Or like what year was created? Like how would you answer the question based on that?
In the past, I've asked questions such as, what does the oil drop experiment tell us about the atom? So in that case, it would be the charge and the mass of electron. I could also say, in more of a short answer type question, explain why the oil droplet would float in the oil drop experiment, something like that. That's really, I think, the only ones that I would, that type of thing. I wouldn't ask necessarily for the name of the person or the year or anything like that, so I wouldn't be concerned with that type of stuff. It's more just the general knowledge. The important thing about this really is the information that comes out of it. Okay. And what would that information be? So the charge of an electron, we're chemists, we like things simple. So we say the charge is -1. If you want to get into the metric system and so forth, there is an actual value associated with it. Physics class would probably make you memorize it and so forth. I don't do that. For a chemist, the charge of an electron is 1, and the mass is very, very small, so we say it's 0. Okay, so as far as a chemist is concerned, an electron's charge is -1, and the mass of an electron is 0. And that comes out of this experiment. Now, at the same time, similar experiments were done with protons. So if you imagine this is all done with this negative charge, you can do something similar with a positive charge going through it, especially the cathode ray experiment. So we also found, at nearly the same time, the second particle of an atom, and that's a proton. So the proton, so let's say type proton, electron, symbol, not very complex, P and E form, and then the mass, charge, location. So I guess we'll just do electron first. So electron, the mass of electron is 0, and the charge is a -1 in our chart here. The same time the proton experiments were going on, we found out that the mass proton is 1 AMU. AMU stands for atomic mass units. It's not really a metric thing, but I don't want you guys to remember the metric values for this. So we just say the mass of a proton is 1. And the charge was actually relatively close to the electrons, if not the same. It just had the opposite sign. So the charge of a proton is a +1. So from these experiments, we looked at the electron example ones. We were able to figure out the mass and charges of these two particles. The last particle in the set is a neutron. Neutrons took much longer to find because they don't have a charge. I guess I wrote that. So the charge is 0. So we couldn't play these same games with charges and electrical fields with neutrons because they don't have an actual charge associated with them. So the symbol for a neutron is N, and the mass is actually 1 as well. It's the same as a proton, as far as chemists are concerned. There is actually a subtle difference between the two in terms of masses, but for a chemist, we just say they're both 1, and we leave it at that.
Is this chart in the slides as well?
Yeah. It's also in the books, and you can find it just about there. There's our chart. Okay, so question, yeah.
Is only the photons measured in AMU?
Oh, no. It's called atomic mass unit. To be perfectly honest, it's kind of a made-up number to make the mass be 1. Like, it's, yeah. It's really just a convenience thing. So it makes our life a lot easier though, so we don't mind. Okay, so finishing up the oil drop experiment. The oil drop experiment went and figured out the mass and charge of electrons, and the way that it did this was by balancing this electrical interaction with the force of gravity, which we understand. Electron has a charge of -1 and then a mass of 0 as we go through it. Okay. One more. You guys feel like you have one more to finish up in you? I'm seeing actually people shake their head yes. So, okay, great. This is the gold foil experiment. Now, it's still named the gold foil experiment because they used the gold foil to do the experiment with. The reason why they use gold foil is because you can make it very, 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 very thin. Anyone ever use gold foil to like cover something? Like you go to the Hobby Lobby or someplace and you buy gold foil, you can get super, super thin stuff here. So when we were talking about the atom, remember we thought that we had this smear of positive spread throughout, and then we had negatives throughout. So the positive is the protons, so you would have mass spread throughout the whole atom here. So if you think about this, if I shot another particle at it, if I shot some sort of particle at it, it's going to hit mass and then bounce off in some direction. And this is what this experiment was supposed to prove. We have here, it's called an alpha particle. It's really, just think of it as something with mass. It's shooting down, and it should hit these atoms of gold and then bounce off in weird directions. Just like if you're shooting pool and two pool balls meet, they bounce off one another, right? That's the idea. But what we found instead is that when we shot these particles here, most of them went through. Okay? Most of them went completely through the gold foil without actually hitting anything. So if I had atoms, So you had another atom packed in here like this and so forth. How could they do that? So what they ended up doing was they had to change their overall idea of atoms and the shapes of them. So they believed that mass was evenly spread throughout. Well, from this experiment, they found out that that's not actually true. And instead of being spread throughout, the mass is contained in a small area. Generally, we say in the center of the atom. So that way, if this particle is shot at the atom, all of them that don't touch that center pass right through, but the ones that touch the center bounce off. And this explained exactly what we saw in the gold foil experiment. Most of, 99% of the particles shot at the gold foil went straight through. But then every once in a while, there was this rare one that would actually bounce off in some direction. This bit of mass in the center of the atom is called the nucleus, and it contains the protons and neutrons because they have the mass associated with it. Also from this, we were able to figure out that it's positively charged, but that shouldn't make much of a surprise to you, because if the center of the atom, the nucleus, has protons and neutrons are positively charged and neutrons are not, so the overall thing should be positively charged. There's nothing to cancel out that positive charge there. So that is the discovery of the nucleus, and I think that's where we'll end today, and we'll pick up there next time and talk a little bit more about the implications of it going into the next section.